Uh, Today, I would like to talk about a paper which offers somewhat unusual perspective on how to teach special relativity. Let me show you this paper. Um, it is written by John Bell, um, who is famous for Bell's inequalities, which are used to prove the quantum nature of reality, quantum nature of our world. And the corresponding experiment is what people have recently received Nobel Prize for with entangled pairs. So I haven't come across this paper myself. I actually um, um, heard about it from my friend uh, from Inductica. And in this video, the censorship of government science and how to break free. It's a very good video. I recommend it a lot. And he mentioned this paper in it. So I decided to have a look. So it's titled How to Teach Special Relativity. I decided I will reduce the beginning because it has this jump start, which is supposed to ignite your interest. And then I'll try to review the rest. Okay. I have for long thought that if I had the opportunity to teach this subject, I would emphasize the continuity with early ideas. Usually it is a discontinuity which is stressed, not a radical break with more primitive notions of space and time. Often the result is to destroy completely the confidence of the student in perfectly sound and useful concepts already acquired. If you doubt this, then you might try the experiment of confronting your students with the following situation. 3 small spaceships A, B, and C drift freely in the region of space remote from other matter without rotation and without relative motion, with B and C equidistant from A. Figure 1. Okay, very simple so far. On reception of signal from A, the motors of B and C are ignited and they accelerate gently. Figure 2. Here. Okay, so far so good. Let ships B and C be identical and have identical acceleration programs. Then, as reckoned by an observer in A, they will have at every moment the same velocity and so remain displaced one from the other by fixed distance. Suppose that a fragile thread is tied initially between projections from B and C. Figure 3. Okay, this is the thread. If it's just long enough to span the required distance initially, then as the rocket speed up, it will become too short because of its need to Fitzgerald contract and must finally break. It must break when at sufficiently high velocity, the artificial prevention of the natural contraction imposes intolerable stress. Okay, is it really so? He asks. This old problem came up for discussion once in the CERN canteen. A distinguished experimental physicist refused to accept that the thread would break and regarded my assertion that it indeed would as a personal misinterpretation of special relativity. We decided to appeal to the CERN theory division for arbitration and made a not very systematic canvas of opinion on it. There emerged a clear consensus that the thread would not break. Of course, many people who give this wrong answer at first get the right answer on further reflection. Usually they feel obliged to work out how things look to observers B or C. They find that B, for example, sees C drifting further and further behind, so that a given piece of thread can no longer span the distance. It is only after working this out, and perhaps only with a residual feeling of unease, that such people finally accept the conclusion which is perfectly trivial in terms of A's account of things, including the Fitzgerald contraction. It is my impression that those with a more classical education, knowing something of the reasoning of Larmor, Lorentz, and Poincare, as well as of Einstein, have stronger and sounder instincts. I will try to sketch here a simplified version of the Larmor-Lorentz-Poincare approach that some students might find helpful. Okay, and that's what he offers. Um, his idea is to just always look at what happens in the frame of A and think from his perspective uh, what's happening when objects B and C move. Um, the point is, well, all of these objects are actually made out of atoms and they hold together by electromagnetic interactions. So each charge um, creates electromagnetic field, which and other charges can interact with. And he asked the question, well, okay, if the charge starts to move, how this field look like? Um, and he says, well, if you just good enough in solving the Maxwell equation, you can do it, right? Here's the answer. It's for the charge moving in direction z. Um, so we see that if we draw a picture, that x and y, the field in x and y direction, and how is now getting stronger by the Lorentz factor. So picture look like somehow like this. If this is a stationary charge, produce symmetric, spherically symmetric electric field, and this is a charge moving in direction z, and it looks like its field got kind of compressed like this. Um, Now we may ask, okay, then if this is a field of an atom, right, or field of the nuclear, the proton inside some atom, and the electron used to, circle around it more or less, if we assume some classical perspective, what will happen to this electron, and what will happen to this atom? I don't know whether it's clear or not. He invites the reader to solve the corresponding equation using computer, but here's the result. The orbit will now be stretched. It won't be elliptical anymore. Stretched in the orthogonal direction, orthogonal to the direction of motion. I don't know, maybe there is an intuitive way to see it. After all, if you imagine um, the field being stronger here, this means the the orbit has to become more curved, right? So the field curves the orbit, right? Um, that's why it's stronger curved. The ellipse is stronger curved on top than in front. So this is more or less intuitive. What's probably less intuitive is that, yeah, this orbit is performed in a period exceeding the original period by a factor, which is a time dilation factor due to Larmor. And and basically his point is that these two facts explain um, the time dilation and length contraction very neatly from the point of observer A. Then when this body is moving at a very fast speed, these effects become more visible, more pronounced, and we see that because every single atom inside the solid body is now kind of stretched, uh, the whole body stretches together. And because um, every single atom has its orbit um, period increased by this factor, like the time moves slower. That any clock, physical clock made out of physical atoms, there in this moving with this body, has its time ticking slower. Um, that's the idea. And of course, he says that um, yes, this fact was actually trivial because we know that Lorentz transformations um, is a symmetry of the Maxwell equation. Um, but conceptually, you could think that um, they just come later as a convenient tool. That indeed, if we perform this transformation, z prime, x prime, y prime, t prime, then we see that um, in this coordinate, the field of the moving charge looks like the field of a stationary charge. So if we indeed moving with a constant velocity v, wherever it is absorbing some charges on the on this ship, yeah, or whatever this solid body is, he sees them. He sees the charges, the fields as fields of stationary charges. So everything is consistent. Um, the difference in perspective is that um, he think those previous people before Einstein was thinking um, about Maxwell equation as fundamental and the Lorentz transformation as secondary. Whereas in Einstein we kind of flip this perspective upside down. Um, Here he also explains that the observations of the person moving with the ship, which he made in respect to us, could also be explained by all these contractions, because um, this person on the ship is contracted himself, and his clocks are moving slower, yeah, and um, he observe us in a certain way, um, and by symmetry, we see that um, he will also see us contracted, and he will also think that our clock uh, moves slower. The That's the idea that sometimes it's useful um, for your intuition to explain things from mm, the perspective of one observer. That in some sense, this Lawrence was trying to prove what Einstein postulates, that all physical laws are the same in all inertial reference frames. So that's the summary of the paper. I don't know whether you see anything new here, because in some sense, yeah, of course, we all knew that you could think about it like that, and if you are an observer A here, you have to think about it like that, right? Um, you have to reconcile the Einsteinian picture uh, with the picture perceived by just some single observer which lives in some reference frame. And this solution of Maxwell equations help you out with this. I guess that's it for today. Yeah, I don't know about the experiment itself with this thread. I always consider it's very confusing. Um, I never liked all this mm, thought experiment involving some sort of unphysical objects like the thread, which is like will break as soon as it got a little bit extended. Because again, looking at this orbits, it becomes even more unclear actually what's exactly going to happen. Like it all it if all the orbits in this thread become like elliptical, all the electron orbits, does it mean it contracts and now it breaks or what? Or what exactly happens? That's actually not that clear to me. So I would like to know what do you think about this experiment and does it even make sense or just some unnatural arbitrary question which could not have a well-defined answer at all. Yeah, okay. I guess see you next time.